Welcome to UGC lecture series in computer science. We are going to see a series of lecture in the subject operating systems pertaining to the BSc graduate students belonging to 5th semester paper 8. So in which we are going to see unit 2. This unit 2 consists of many different sections, out of which we are going to see topics on deadlocks. We have already covered 2 different sessions on deadlock. So this will be the third session of deadlock, in which we have seen what is a deadlock, what are the characterization of deadlock, what are the methods of handling deadlock, what is a deadlock prevention, what is a deadlock avoidance, how to detect a deadlock, and what is the recovery procedures if a deadlock situation has occurred. So in which in today's session we are going to see the examples for the deadlock prevention and for the deadlock avoidance, wherein we are going to concentrate on 2 different topics. One is banker's algorithm, second one is an philosopher's problem called as dining philosopher's problem. Now, what do you mean by a banker's algorithm? Before going on to this topic of banker's algorithm, what people do in a bank? If I want to take a loan, say for example, if you are going to construct a house, and if you have estimated the cost of house construction will be somewhere around 10 lakhs for an example, and you go to a bank, do you think the bank employee or the bank manager will be allocating the entire 10 lakhs whatever you ask for? Definitely not. He will be allocating a resource wherein he will be allocating either 1 or 2 lakhs based on the income proof that you have shown to the bank. And do you think that the bank does not have sufficient funds, or the bank does not or the bank is not capable enough to give you 10 lakhs? No, even that condition is also wrong. The bank is capable enough of giving 10 lakh rupees, but they will not give you 10 lakh rupees as you have asked for. They will give you a minimum sum of 2 lakhs or 3 lakhs based on the income that you give. Okay, why do they give only 2 lakhs or 3 lakhs? What are they going to do with the other amounts? They have to decide in a factor that they have to allocate to someone else. In supposing if the other person, say for example, if a person by name B comes in and if he is going to ask for some amount, so the bank employees have to equally allocate the money even to the next person. So that is the reason they are not giving the entire amount to you, and they are going to give only a part of sum that has been assured. So that is the overall concept of the banker's algorithm. How they are going to act, what they are going to give, and how you are going to repay it. So they will be giving you a fixed interest scheme and variable interest scheme, provided they will be asking you to pay the entire sum of money within the stipulated time. So on a mutual agreement basis, like either both the bank, they will be agreeing to a point that as a customer you will be required to pay the amount within a period of 10 years or within a period of 20 years, or as assumed by the or as given by the bank. And the customer, when they are drawing the money, they will be having it in their memory that they will be receiving only some 2 lakhs or 3 lakhs, and they are supposed to pay within the scheduled time. So on a mutual agreement basis, the bank and the customer works on. So we will relate this example with respect to a system. First of all, we will see what a banker's algorithm is, what the definition says, and then we will relate it to an example. Here, the banker's algorithm is used when there exist multiple instances of a resource type. Each process must a priori claim maximum use. When a process requests a resource, it may have to wait. When a process gets all its resources, it must return them in a finite amount of time. Now, in the first point, it says that it is used when there exist multiple instances of resource type. Second point states each process must a priori claim maximum use. So it means that you are going to have a maximum claim. You are asking for the maximum resources, and the banker is allocating a minimum set of resources, and how you are going to use it. What is the priority you are going to use the fund. And it does not mean that always whenever you go to a bank and whenever you ask the banker for a lump sum of money, it does not mean that he needs to give you at a particular instance of time whenever you ask for. So if he is not going to give you at one particular time, you are supposed to wait in queue, and then when your turn comes in, you are supposed to get the money. So that is what the third point even says. And here the algorithm determines whether a given state of system is safe or unsafe. The state of system is represented by the current allocation of resources to processes. The state of system is represented, thus the state consists of two vectors, resource and available, and the two matrices claim and allocation. Now in our previous session we have seen what is a safe state, what is an unsafe state. What do you mean by safe state? Say for example, if you are going to ask for 10 lakhs, or if you want to have a function, if you are going to have a function and if you think that it will cost 10 lakhs of money for conducting the function, and if you have sufficient amount of funds, something like 25 lakhs of money in your account, then you can very well happily you can conduct the function because you have enough amount of money. That is called as, such a state is called as a safe state, wherein there will not be any sort of deadlock conditions to occur. Whereas in the case of an unsafe state, supposing in the same condition, if you are going to conduct a function which will cost for 10 lakhs, and if you have only 2 lakh of rupees, then you will not be in a position to conduct the function as you thought of. But it does not mean that always this situation will result in a deadlock. Supposing your friend comes in and if he is going to help you out of the remaining 8 lakh rupees, then definitely you can conduct this function at ease. So this state is called as an unsafe state. This unsafe state, it does not denote that it will result in a deadlock, but it may result in a deadlock. So there is a possibility of it may result in a deadlock. Such a state is called as an unsafe state. So similarly, when we relate this example to a banker's algorithm, wherein in the banker algorithm, as far as the mutual agreement made by the customer and the banker is that the customer will be paying the amount, will be repaying the amount in a reasonable amount of time. If he is not going to repay the amount, what will be the next? So that becomes an unsafe state. If he is going to repay the amount, okay, so within stipulated time if he is going to repay, then that is said to be a safe one. So now here in this it says that both about the safe state and the unsafe state. Here a safe state is one in which there is at least one sequence of process that can finish if granted the resources they need. That is, at least one sequence that does not result in a deadlock. An unsafe state is a state that is not safe. Then this banker's algorithm, how does the banker algorithm operate? It operates in two modes. Either it says yes, you can proceed, or no, quit, you are not allowed to go about it. So this banker's algorithm operates in two ways. One is, for all the processes, is there a process that can finish with the available resource? Yes. If you say the process is yes, then assume that the process has finished and add its resource to the available resource. Continue the check for the remaining process. If you say no, no means it is a deadlock situation. If you say it is a deadlock situation, then quit and you come out. So this is how it operates. Now let us say what are the basic facts relating to this banker's algorithm. The first fact is, if a system is in safe state, then there is no deadlock. If a system is in unsafe state, then there is a possibility of deadlock. It does not mean that definitely there will be a deadlock. There is only a possibility of a deadlock. Then the third point is the avoidance. Ensure that a system will never enter into an unsafe state. If you are going to have sufficient amount of money with you, then it does not mean that your state will never end into a deadlock state. So that is called as, and that is the meaning of the third point. Then we will relate this example with respect to an operating system, with respect to a real-time system, how it's going to work out. So I said you are required to have two different matrices. One is the claim matrix, other one is the resource and the available matrix. wherein you also require the need matrix. Then now let us relate with the real-time problem. Here, as far as this example is concerned, you have 5 processes and 3 resource type A with 10 instances, and resource type B requires 5 instances, and resource type C requires 7 instances. Now this is the allocation matrix and this is the maximum availability matrix. So now you are asking for, say for example, this guy, let us consider this A, B and C are said to be 3 different persons. This guy A is asking for a maximum of 7 lakh rupees from the banker, and this B is asking for 5 lakh rupees, C is asking for 3 lakh rupees. So the allocation matrix states that here for A they are not allocating any amount because he is not showing any sort of income proof, and for B they are allocating 1 lakh rupees, and for C they are not allocating. So what is the need then? Supposing if for B, if they are going to allocate, if the bank is going to allocate 1 lakh rupees, then what is the remaining? How much he needs to manage in order to complete his task? So he requires 4 lakh rupees to complete the task. So that is said to be the need matrix. So in our next example here, this shows how it is getting deducted. Say for example, I said he requires 7 lakh rupees, A requires 7 lakh rupees, wherein here for the process 0, no amount has been given by the banker, and this B requires 5 lakh rupees wherein the bank gives 1 lakh rupee, C requires 3 lakh rupees wherein it is not giving any amount. So what is the need? So again A requires 7 lakh rupees wherein it has not been given at all, and since 1 lakh has been given by B, then it requires the remaining 4 lakhs, and C again it's not been given, so it requires 3 lakhs. So this is for the first instance, first process, and for the consequent processes, if some amount has been allocated, then definitely it is getting reduced from the banker's point of view. And then after allocating all these resources, how much is available in the bank? This much amount is available in the bank. So this is used for repayment purpose. Now what are the drawbacks of banker's algorithm? So now we have seen what a banker algorithm is, how it is working. Now let us see the drawbacks of the banker's algorithm. As far as the drawbacks of banker's algorithm is concerned, the processes rarely know in advance how many resources they will need. Number of processes changes as time progresses, and the resources once available can disappear. The algorithm assumes processes will return their resources within a reasonable time. Processes may get only their resources after an arbitrary long delay. So practical use of this banker's algorithm is pretty rare. Now let us see the restrictions for a deadlock avoidance, and then what are the restrictions for the banker's algorithm. So what are the restrictions for a deadlock avoidance? Here this was an example that was given for avoiding a deadlock situation. This banker algorithm was an example that was given for avoiding a deadlock situation. So what are the restrictions? Here the maximum resource requirement for each process must be stated in advance. That is, as far as a banker algorithm is concerned, for your requirement you are supposed to state the maximum requirement. You are supposed to state that I require 10 lakh rupees for building my building, for building my construction, right? So that available resources you are supposed to give it in advance. If you are going to say, sir, I require this much of money, then if the bank is pretty enough to give such a money whatever you are claiming for, and if much of resources been available from the bank, then definitely they can help you out. Then definitely there will not be a situation of deadlock at all. Then the second point here states that the processes under consideration must be independent. That is, the order in which they execute must be unconstrained by any synchronization requirements. And this is self-explanatory. So let us move on to third point. There must be a fixed number of resources to allocate. No process may exit while holding resources. Supposing we are going to get some money from the bank, and supposing we are not going to repay at all, then the bank cannot go under a loss. So you are supposed to repay, and you cannot exit when you are going to hold the money. You cannot exit when you are going to hold some sort of resources with you. That is restriction on deadlock avoidance. Then what are the banker's algorithm for deadlock detection? Here in the first point, the algorithm looks for a process that can finish within the currently available resources. Supposing the bank gives, like if it is going to ask you, you are supposed to repay within 10 years, and if you have repaid within 5 years of time, then it is you have completed your task. And the second point denotes, then it assumes that the process has finished, marks the process and adds its resources to the available vector. What does it mean? So if you are going to pay the entire amount within the stipulated time, the amount has to get repaid in the stipulated vector. In the bank, the amount has to get deposited in such a way that there is no nil balance is available with the customer, and the bank has got all the resources, all the fundings back. So that is a restriction. Now the next topic, what are the approaches for recovery? Let us see what are the approaches for this kind of deadlock recovery. Here the first point states, abort all deadlock processes. If a deadlock has happened, how to recover? First, abort all deadlock processes. Back up each deadlock process to some previously defined checkpoint and restart all processes. Successively abort deadlock processes until deadlock no longer exists. Successively preempt resources until deadlock no longer exists. Supposing if a deadlock has happened and you are not able to recover at all, say for example, in your system, in your computer, when you are working, at times there is a situation you would have encountered wherein your system may get hanged, and even after pressing the alt control and alt control delete button, your system, the hang may not go out. So what will you do? You go for a hard reboot, you go for a you press the reset button and then you restart the computer. So supposing a deadlock has happened, then close all the work and then reset the issue. And supposing if you have resetted and if you have checked all the conditions have been working fine, then if you think that there is no concept of deadlock being happened, then you can work out as usual. So these are the approaches for recovery. Then coming to the next topic, it is called as the dining philosopher's problem. What is a dining philosopher's problem? Where it is used? So this dining philosopher problem, the working of dining philosopher is like wherein limited set of resources, that is the processes, try to occupy the limited set of resources. That is the concept of the dining philosopher's problem. Let us relate with the topic relevance. Let us give a topic relevance. What do you mean by a dining philosopher? Let us consider there are 5 philosophers who are sitting around a table wherein they wanted to have a meal, they want to have a lunch, and the rice is being kept in a bowl centrally across the 5 different philosophers. So the condition here is, for each and every plate there is a chopstick, there is a fork available. So the condition is they are supposed to use both the chopstick and the fork at a time. So alternatively this is being placed. So there are 5 philosophers sitting. How many philosophers do you think can eat at a time? That is said to be the dining philosopher's problem. So if they are not going to eat, what is the problem that they are going to face? They will be facing 2 problems. One is either they may encounter in a deadlock situation, or they may encounter in a starvation, or they may encounter in a live lock situation. We will explain all those situations. Now let me read out the problem statement. 5 philosophers sit around a circular table. Each leads a simple life, altering between thinking and eating rice. In front of each philosopher is a bowl of rice that is constantly replenished by a dedicated waitstaff. Now there are exactly 5 chopsticks on the table, one between each adjacent pair of philosophers. Eating rice in the most proper manner requires that a philosopher use both adjacent chopsticks simultaneously. So develop a concurrent program free of deadlock and indefinite postponement that models the activities of a philosopher. So this is how it looks like. So in the center, let us consider there is a rice bowl and these are the chopsticks. So each and every philosopher who sits at the corner of the table has to use both the chopsticks. So if this philosopher is going to use two chopsticks, then this philosopher will not be in a position to use the right chopstick, the chopstick that is at his right. And if he is going to use, this philosopher will not be able to use. So from this diagram, how many philosophers can eat at a time without causing any deadlock is the problem. So here, so let us consider these philosophers to be the processes. The chopsticks are said to be the resource available. So the idea of this problem is to capture the concept of multiple processes competing for limited resources. Now, what are the situations, what were the problems with respect to a dining philosopher is either the chopsticks, either they need to start eating or they have to stop eating. Now, what do we worry about? What may happen? May end up into three different situations. Either the philosophers may starve, or the philosophers may end in a deadlock, or the philosophers may end in a livelock. What do you mean by the philosophers may starve? How do they starve? So if there is a 5 philosophers are sitting and if they are supposed to use 2 chopsticks at a time, then when you could practically think of it, only 2 philosophers at a time could use both their chopsticks and they could eat their bowl of bowl of rice, the rice that has been kept on their plates. So at a time only 2 philosophers could eat. So what does it mean? The remaining 3 philosophers have to starve, have to wait till these 2 philosophers keep their chopsticks down on the table. So after they kept, the other philosopher will take the chopstick and then he will eat from his both his hands. So till first philosopher completes, the other philosopher has to wait in a